All right, so now let's talk about some applications of exponential functions. There really are genuine, like real world applications of this. They're not just like made up for an algebra class. Okay, in real life, you can use exponential functions in quite a few ways. So the first is compound interest, money. All right, so here is the compound interest formula. Does this look familiar? Yes, it does. We've got a number here, another number here, raised to something where we have an x, the variable is in the exponent, right? In this case, our variable is t for time, and that's in the exponent. So this is an exponential equation. So what does this mean? A of t is going to be the amount of money that you have, the account value. P is our starting account. So T is measured in years. P is our starting amount or the principal. P stands for principal amount. That means your beginning amount or the present value. R is the annual percentage rate or APR. You might have heard that phrase, APR. That's your annual percentage rate. And N is the number of times that it's compounded in 1 year. So we'll do some examples. So that's a lot of different things to keep track of. Okay, and N shows up twice, right? So if you had $1,000 and the APR, the percentage rate was 10%, the more often that it compounds, the more often they pay you interest, the more money you make, right? So if annually, they compounded it annually, 10% of $1,000 would be $100, and you'd have $1,100, right? But what if they did it twice a year, semi-annually? You'd have a little bit more. What about if they did it quarterly? You'd have even more. Monthly, more. And daily, you'd have $5.16 extra compared to if they did it annually. It's not like a ton, but still free money. So the more often that something compounds, so N getting bigger, gives you a bigger value out here. Okay, so let's do an example. If we invest $3,000 in an investment account, paying 3% interest compounded quarterly, and that's like pretty standard, how much will the account be worth in 10 years? All right, so what do we have? We have $3,000 is our principal amount. 3% is our APR, or R value. It's compounded quarterly, and they want to know in 10 years how much it's going to be worth. So here's our equation. So we're going to put 3,000 in for P, 0.03 in for R. This is a place that it's easy to make mistakes, is like putting 3 instead of 0.03, right? And for R. 4 is how many times a year it's compounded. And T is how long we're going, 10 years. So over 10 years, in 10 years, the account value would be $4,045.05. Okay, so really this is just figuring out, okay, which of these values do I put where, right? What's my N, T, R, and P values to be able to find the amount in my account. All right, 529 plans. A 529 plan is a college saving plan that allows relatives to pay to invest money for a child's future college tuition. Lily wants to set up a 529 account for her new granddaughter and wants the account to grow to over $40,000, or she wants it to be worth $40,000 in 18 years, which maybe her grandma thought that would be a lot of money for college, but if you're applying for college recently, that's like lunch on Tuesday, right? Anyway, very nice of her grandma at any rate to try to save that much money for her. So in 18 years, she wants it to be worth $40,000. The account, she's assuming, again, we never know about these things looking forward, but she's assuming it's going to earn about 6% interest. R is going to be about 6%, compounded semi-annually or twice a year. To the nearest dollar, how much will Lily need to invest in the account now? You could pause it and try to figure that out. All right, so let's do this together. We don't know what P is, right? P is what we want to solve for. How much do we need to put into the account? If we know that A of T, we want that to be $40,000. R, they tell us, is 6%, so R is 0.06. And it's compounded semi-annually, so our N is 2. And T is 18, right? In 18 years, how much will it be worth? So now we just simplify this, simplify that, divide, right, to solve for P, and we find that our principal is $13,801, which is pretty great, right? If you had $13,000, you just plopped it in there. In 18 years, you'd have $40,000. It's awesome. Okay, so we've talked about different compounding rates. So what if you just had $1 and it was invested at 100% interest? I mean, not very realistic, but whatever. For 1 year, how much money would you have at the end of the year? Well, annually, you'd have $2. Semi-annually, you'd have $2.25. That's a big difference. Quarterly, you'd have $2.44. Still kind of a lot. Monthly, $2.61. Daily, $2.71. So it's getting to be like less. Hourly, I mean, it's like a little bit more. Once per minute, it gets to be that. Once per second, it gets to be that. What do you notice? Well, this isn't changing very much. All right, once we get to like compounding very quickly, it looks like it's not like it's going to just keep getting bigger and bigger, which makes sense, right? That would make sense if you compounded it like 1,000,000 times a second. With starting with $1, you're not going to end up with like $1 million at the end of the year, or at the end of the year, right? There's a limit to how much money you'd have if you started with $1, given a compounding rate. Okay. That number has a name. It's called E. So E is an irrational number, kind of like pi, right? Pi is a number. We just use that symbol pi to represent it. E is the same. E is a number. Okay. Here's what it is. It's like 2.718282, and it goes on forever, just like pi. Okay. It's irrational. It goes on forever, but it's about equal to 2.72, right? And the definition is it's the limit when n gets really, really, really big, this approaches that value, this expression, 1 plus 1 over n to the nth power approaches that value. And you could try that. Put in like 1,000 for n, put in 1,000,000 for n, put it in your calculator and see what you get. It should be getting closer and closer to this value. And this actually shows up in all kinds of places. So it's like pi. It's like this irrational number that shows up in the natural world. So it's so important that your calculator has an E button. And that's how you find powers of E or use E in equations. So like if you wanted to find E to the 3.14, see what they're doing there? That looks like pi, right? E to the 3.14, calculate what that is and round to 5 decimal places. And you might want to just make sure you can do that. Take out your calculator, find the E value. So this is just like if it was 2 or 7, right? This is just a number raised to a power, and your calculator should tell you that value. Okay, so as we saw, E is what happens when continuous compounding happens, right? So if we have continuous growth or decay, we use this formula, okay, which is a lot simpler. Instead of 1 plus r over n, we just have E. So again, this is still an exponential equation. A is our initial value. E is E. R is our rate of growth or decay, and T is our amount of time. So sometimes R can be big. So far, all of the examples we've used are things growing, like populations or money, right? But things can also decay or there can be less and less. So things that decay exponentially are like radioactive elements. They decay exponentially. And a lot of examples about exponential decay are with radioactive elements. So in business applications, it's the exact same formula, except instead of A, they call it P, but it's the same thing, right? P is the principal, R is the growth rate, interest rate, and T is the time period. And again, so with money, hopefully it's always growing. But with R, if R is less than 0, if it's negative, then we've got exponential decay, and we'll do an example of that. But first, let's do back to money. So you got $1,000 invested in an account earning 10% a year, compounded continuously. How much is in the account at the end of a year? All right, so here's our equation. P we know is 1,000. R is 0.1, right? 10%, we write that as 0.1. And at the end of 1 year, T is 1, right? So we just plug these values into our calculator and we get this equation, or this value, right? $1,105.17. All right, now we've got decay. So radon-222 is a radioactive element, and it decays at a constant rate of 17.3% per day. And this actually is true. And it makes sense that something like a natural element, something happening in the real world, isn't going to decay quarterly or on the hour, right? It doesn't have a watch. It's just constantly decaying, right? So it makes sense that in this case, E is a very natural, that limit is a natural thing to use. So how much, if you start with 100 milligrams, and just let it sit there, after 3 days, how much will you have? All right, so here's our equation. Our A, our initial value, we know we start with 100. T, so in this case, it's our rate of decay is per day. So our T is just in terms of days, right? So we are after 3 days, our T is 3. And what's our R? Our R is the decay, so it's a negative value, and we write that as 17.173, right? So negative 0.173. And again, we just plug this into our calculator and get this value. So yeah, 40% of it's gone after 3 days. Right, and that was the last example. So in your homework, you'll have some word problems that you need to use these equations to solve. Let me know if you have questions.